Ever wonder what really goes into building the apps on your phone or the websites you use every single day? It's definitely more than just a flash of genius and some late night coding. So let's dive in and demystify the world of professional software engineering. First things first, let's talk about scale. Software isn't just a big industry, it's an absolute global economic powerhouse. In every developed nation, the money spent on software is a huge chunk of the entire economy. To put it simply, our modern world literally runs on code. But here's the thing, for all the money we pour into it, making good software is incredibly difficult. Way too many projects end up costing a fortune, they're unreliable, and they just don't do what we need them to do. And that is the fundamental problem that software engineering was created to solve. So, if the solution isn't just about writing more code, what is it? Well, the answer is to treat software development like a real engineering discipline, one that brings order, predictability, and, most importantly, quality to the whole chaotic process. And what's really key here is the scope of that discipline. The official definition says it all. Software engineering is concerned with all aspects of software production. We're talking about the entire journey, from that first back-of-the-napkin idea all the way to supporting and maintaining that system years and years after it's been launched. It's the whole shebang. People get software engineering and computer science mixed up all the time. Here's a good way to think about it. A computer scientist is like an architect who understands the deep theory, the physics behind how a bridge stands up. But the software engineer? They're the civil engineer who actually goes out there and builds the bridge, dealing with real-world stuff like budgets, deadlines, and tricky terrain. And the very first step in building that bridge isn't pouring concrete or laying steel. It's creating a detailed, bulletproof blueprint. In the software world, that blueprint comes from deeply understanding what the user actually needs. This stage is without a doubt the most critical part of any project.
This whole process has a name: requirements engineering. Before anyone even thinks about writing a single line of code, engineers have to figure out precisely what the system needs to do. What services does it have to provide? And what are the constraints? The budget, the timeline, the kind of hardware it needs to run on. Getting this part wrong is probably the #1 reason software projects fail.
So how does it actually work? Well, it's a real process. It kicks off with discovery. That's basically talking to everybody involved to figure out what they really need. Then, all those scattered ideas get sorted and organized through classification. After that, the team has to do some prioritization and negotiation because you can't build everything at once. And finally, all of that is locked down in a formal specification. That's the official blueprint for the whole project.
All right, so blueprint in hand, how do we actually start building the thing? Turns out there's more than one way to do it. Different kinds of projects need different approaches, or what we call process models. Let's take a look at 2 of the big ones.
First up, we have the old school classic, the waterfall model. It's super linear, very plan-heavy. You have to finish all the requirements first. Done? Okay, now you finish all the design. Done? Now you do all the coding. It's a one-way street where each phase flows down to the next, just like, a waterfall. It's rigid, for sure, but for projects where you know exactly what you need from day one, it can work pretty well. But what happens when things change? They almost always do, right? That's where incremental development comes into play. Instead of trying to build the entire system in one massive go, you build and deliver it in small, usable chunks. You'll specify, develop, and test just one little piece, get some feedback, and then you move on to the next. And here's why that is such a game changer. With that old waterfall model, if you need to make a change late in the game, it's ridiculously expensive. You might have to go all the way back to the start. But with an incremental approach, the cost of making a change is way lower because you're course correcting all the time. It's kind of like the difference between trying to turn an oil tanker versus a speedboat. This really powerful idea, this ability to not just tolerate change, but to embrace it, led to a full-blown revolution in the software industry. It's the philosophy that dominates today: Agile. Now, Agile isn't just one specific method. It's more of a mindset. It's all about valuing responding to change over blindly following a plan. It's about getting working software into people's hands quickly, rather than writing endless documentation. And it's about constantly talking and collaborating with the customer. The whole goal is to deliver value, fast, and to be able to pivot on a dime. One of the most popular ways to actually do Agile is a framework called Scrum. And if you're around a software team, you're going to hear these terms all the time. The product backlog, that's the what. It's the master to-do list for the entire project. The sprint, that's the how. It's a short, focused cycle, usually 2 weeks, where the team builds a small piece of the product. And the Scrum Master, that's the who. They're like a coach, helping the team and clearing away any obstacles.
So a typical sprint cycle looks a little something like this. The team grabs a few high-priority items from the product backlog. They plan out how they're going to build them, then they spend the next couple of weeks in a focused burst of development and testing. At the very end, they show what they built to the customer, get feedback, and then the whole cycle starts right over again. It's this rapid, repeating loop that lets teams adapt so incredibly quickly.
But, building software isn't just about the technical process or which framework you use. It comes with a really profound professional and ethical responsibility. This is where the engineering part of the name really truly matters. Just like doctors or civil engineers, software engineers operate under a professional code of ethics. This means things like respecting client confidentiality, being honest about what you're capable of, honoring intellectual property rights, and, of course, never, ever misusing your technical skills. These principles are the bedrock that allows the public to trust the profession. And all of this brings us to a final, really crucial question. From our finances to our healthcare to how we connect with each other, software is woven into the very fabric of our lives. So the challenge for engineers today isn't just building things that work. It's about building things we can fundamentally trust. And that's something for all of us to think about.